All right, I think we're good to start. We've got a good audience here today. Good morning, everybody. My name's Thomas Miller, Director of Commercial SATCOM Solutions here at Kratos. We're very happy to see you all here for the demonstration today. And we've got this demo. We're going to do the 3 different demos, and we've got 3 different people. So to my left, Cody.
Hi, Cody Francisco, Director of Tactical Satellite Solutions for Kratos.
And then Bart to my right here.
Bart Leihart, part of the solution architecture team.
Great, thank you very much. So let's dive into this. So I want to keep this fairly informal. So I'm going to go through the presentation and then we're going to dive into the demonstrations. I want to make sure you guys have got a good understanding what we're saying. So if there's any questions, please feel free to stop and ask. If there's some specific questions that's only related to your specific setup, you're welcome to just come and see us afterwards. And if there's some more details you need, we'll be around, so please feel free to come and see us. Okay, let's go. Now, as you all know, we've got a lot of disruption today in the satellite industry. There's a lot of new non-geo satellite companies that's entered into the market. There's a lot of new technologies we see, a lot of disruptive business models. You might know some of the LEO constellations that I'm referring to. That's really disrupting the market at this point. We have to embrace telecom standards to keep up on the satellite side with what's going on in the rest of the industry, integrate with the telcos. And we are looking at things like AI that is forcing us to be more innovative in our thinking of how we can do things faster. So a lot of disruption and changes we're seeing. Now we want to see if we can help you a little bit. How can you be competitive in this environment and make sure your business can thrive? So there's some few basic things that we need to look at. So obviously you want to grow revenue, you want to increase efficiency for your business operations, you want to future-proof your investment, you want to make sure that your capital expenditure today, the technology you use is still going to be relevant 3, 4, 5 years from now. And we're going to help you to show how you can do that. Then you obviously want to decrease cost. So you want to find ways, if you decrease costs, you grow your revenue, then your business can do well. Now there's a quote from a company called Analysis Mason. They did some research in the field of virtual ground, and they said software-defined ground revolutionizes the space network's edge by replacing today's purpose-built and vendor-locked network with OpenEdge devices. And we're going to focus a lot today on the OpenEdge from the OpenSpace Platform and how the OpenEdge can help you to actually be more competitive in the market, how you protect your investment, and how you can move forward with that. So what is OpenSpace? So OpenSpace is the world's first fully virtualized SATCOM platform. It's a platform we can run multiple services on, and it's everything ground related for your satellite communications. How we do that? First, we need to take the RF signals and digitize that, and we convert it to IP packets. Once we've got this RF signal in IP packets, we can now manipulate that by means of virtualization. So we can leverage what's already out there today. The telecom industry is using that a lot. Virtual instances. So you can look at private and public cloud, where you can now run these cloud native functions like virtual modems in the cloud. So that's the next step we want to do. And then the platform then gives you the ability to orchestrate this all together. So you want to make sure that you can automate the services. You want to spin new services up on demand as you need them. You want the ability to shut them down again if you don't need them and use those resources for something else. So that's how we get to the OpenSpace platform. We digitize, virtualize, and then orchestrate that all together. OpenSpace also make use of standards. That's why it's called open. It's not open because it's not secure. It's open because it adheres to all the standards that's out there. Standards like API interfaces, REST, MEF, LSO, and also carrier Ethernet for end-to-end connectivity. Also very important, just want to get back to the digital side. We also adhere to the Diffie standard for the way in which we convert those RF signals into IP packets. So that's a Diffie, is a standard, and that makes sure we're interoperable between various platforms. Any questions so far? Good. Now, how can you be competitive? Let's look at how the edge can help you to be more competitive in the market. So first of all, you want to be able to grow on demand. So you want to spin up virtual modems and network applications as and when you need it. Now, because the OpenEdge platform, as you'll see later on, is based on standard general compute, this enables you to run standard native cloud functions there so that you can run different applications as and when you need it and whatever the customer would like. So you're not locked into specific hardware. Sorry. It enables you to interoperate with the open standards like we talked about. It lowers your cost. It reduces your footprint. It lowers your cost because you don't have to ship new hardware all the time for new applications to remote locations. The OpenEdge can just enable new software that you can even distribute over the air and install, and that also gets you faster to the market. So now suddenly, instead of waiting weeks for equipment to ship out, you can just download software instances, run them, and your service is up in a few minutes. So that really revolutionized the competitive advantage on the edge. Just quickly, the high-level architecture, you can see there, we've got on the left the gateway side, then we have gateway antenna, satellite, and then the OpenEdge is on the right-hand side on the diagram there. So this is where we run the virtual modem and the other applications. So that gives you the context, and then let's dive a little bit into how does the OpenEdge look like. So the OpenEdge obviously has got the digitizer built in and then the virtual modem, one or more virtual modems you can run on the OpenEdge platform. And as I said, that's running on general compute. So standard Intel based in our example here, x86 platform. Now to add some value to that, we can run different applications on the edge. And what we're going to look at today is private 5G, things like multi-orbit solutions with SD-WAN, carrier monitoring. You can run security applications there. Maybe your customer wants some intrusion detection system. You can enable that, or some specialized routing layer 3 functions. So those are all type of examples of applications that you can now run on the OpenEdge platform. So let's look at what we have in the demo room here today. So on my left, we have the gateway side. And just quickly for the guys that can see, I'm going to stand here in the middle so the camera can see. On the bottom side, we have the general compute platform that runs the virtual modems. So just one physical platform. Then we have our management platform in the middle there. And then we have our digitizer that converts the RF into IP packets. And on the top, we've got a network switch to put them all together, to connect them all together. So that is actually a complete hub solution. So that's how small the footprint is and how easy it is to deploy to get you started. Then on this other side there, on your right-hand side, we've got the open edges. And I'm going to ask Cody to quickly explain that for us.
Yeah, sure. So we've got 3 edges here with an embedded digitizer. So each one of those is a super micro x86 compute platform. And in today's demo, the three of them are running three different use cases. So one of them is going to be our private 5G use case. We've got a carrier monitoring use case, and then we've got a multi-orbit use case as well.
Okay, good. Thank you, Cody. Any questions on what we have in the room here today? And then as you can see, there's no real satellite up in the air for us. That satellite is simulated. So we've got the real RF going in the background here from the hub to the remote, but we don't have a satellite. So, but we do have real RF to show that it can actually work. This is not PowerPoint only. As mentioned, we want to focus on those three use cases as the demonstration part today. So that'll be private 5G, multi-orbit, and carrier monitoring. So let's dive into the first demonstration. So private 5G at the edge. So what does that actually mean? And let's look at a use case. So just imagine you have a remote location like a mine. And in this case, we chose an open mine to show you OpenSpace can work in that environment. And in this mine, let's assume there's no other connectivity than satellite for our example. And they want to run a modernized 5G network on the mine to connect maybe IoT devices together. Maybe they want to do local comms, phone calls, and connect Wi-Fi access point, all managed by a private 5G network. The challenge is that if you use this in a normal sense with cellular backhaul over the satellite, then when the satellite link is congested or down, your local network is not going to work because normally the 5G is dependent on that link. In our solution here, we're going to show how you can run this private 5G network that operates independently of the satellite link. Whether it's down, whether it's congested, you will still be able to have local communications. Doesn't matter what the state of the link is. The benefit, so it reduces your satellite bandwidth because all local traffic will stay local. So you're not paying for any 5G traffic that stays local. And the second thing is high availability of business applications. So you make sure that local traffic can always work and be available. Now, this is an example of a complete end-to-end carrier Ethernet solution we have in the room here today. So like you saw, we've got the open edges connected to this side, which is the gateway. And I'm going to switch screens now to show you how that looks like briefly in our Ops Center, which is our management system for the OpenSpace platform. So what you can see here today, and I'm going to see if I can just make this bigger. There you go. This is an example of a dashboard showing us a map with some terminals on there. In this case, there's a terminal here close to Washington, D.C. This old dashboard is very configurable. I'm not going to dive into that detail today. I'm just going to show you another dashboard here, which shows us that carrier Ethernet end-to-end connection. You can see here we've got the virtual modem instance with our gateway feed service, satellite link that's simulated, and then the edge on the other side. So quick overview, very easy for an operator to see what's going on with his network. Now, what we want to look at today, like we said, is the private 5G network. And how did we set that up? So what we did is we took one of our OpenEdge devices and installed a 5G core software on there. So that's a complete 5G core running on the OpenEdge device at the remote location, and this software was provided to us by Druid. The software is called Remus, and we'll show you in a little bit how that looks like. Then we actually connected to that a 5G Node B small cell. And Cody can quickly point that out.
Sure, that's that white square antenna on top of the box there. That's our 5G radio.
So 5G radio, and then connected to that, we have the cell phone, actually two cell phones on the desk here. These cell phones will then connect 5G over the air to that radio. And we also have a 5G CPE device there. Cody is pointing it out, that white box there, that can provide us Wi-Fi access for a laptop that's on the desk here so that we can show some different use cases. For local traffic, we also have a speed test server, and we're going to connect to that to show that local traffic can work fine. As I've shown, this is the carrier Ethernet over SCPC link that's up, and this is when we put that all together on a high level, how this diagram looks like. So you've got the 5G network on the remote side that can make use of the satellite link when it's up to get access to the rest of the world. We also have a speed test server running here at the gateway side, and that's what we're going to use to show that communications can work all the way from that laptop through the Wi-Fi, through the 5G network on the edge, through the satellite link to the speed test server on the gateway side. So what I'm going to do now, I'm going to switch to the camera we have here that's showing you the laptop screen so that you can see the speed test running there. Let's see if that works. There you go. So Sergey is going to start the speed test for us. We've got two there. You can see the dark side one is connected to the gateway side speed test server, and there you can see the speed test running. Now, what I'm going to do is, while that's running, let's switch back to this is our op center, so the gateway side, and I want to look at the data link service here for this specific OpenEdge device that's connecting to the gateway to show you on this graph that we do see that traffic from the speed test on this graph on the gateway side. So that sort of proved to us that the end-to-end connection is working. We can see this traffic going all the way through the gateway side. But we should also be able to see this traffic on the edge. By the way, this is the RF side of the edge. You can see it's locked. And then if I go there to the network, we'll wait for this graph to open, and then we should be able to see the same type of traffic graph here for the speed test on the remote side. Okay, so that shows traffic was flowing through the remote OpenEdge device as well as the hub side. Now let's go to another example. If we say, let's show that this can work from a real phone. Okay, so that was Wi-Fi through 5G. Now we want to do from the phone directly with 5G. So no Wi-Fi involved to show that the 5G network is working. And then I'm going to switch to the camera again. So there's two phones. Again, the darker one is connected to the speed test server on the gateway side. So there you can see it going. While that's going, I'm going to switch to another screen that will show that this phone is actually connected to our 5G core software. So this is the core software, the dashboard for Druid's REMAS core network. And there we can see we get the values there at the bottom. In this case, it was 94 megabits per second, showing that the traffic is actually flowing through this 5G core running on the OpenEdge. We can also see that this this core has got a CPE connected, which is the Wi-Fi CPE there, as well as the two cell phones. Now again, if I look at the edge here, we should be able to see the traffic there, and you can see the traffic that flowed through the edge for the speed test coming from the cell phone in this case. Now let's say, like we said in the beginning, we lost our satellite link. So let's say something happens, we've got rain fade or a big storm coming in, or the link's congested, and we cannot use that anymore. Now we want to make sure that we still have our 5G network active. So what I'm going to do for that is I'll just go to the edge. Let me get my right screen here. There we go. And on this edge, I'm going to go to the setup side and just disable the lock here. Let's get there. So I disable the transmit. So this is now going to simulate the satellite link being down. All right, now the satellite link is down. Now what we want to do is we want to demonstrate that with our link down, we can still have local 5G communications. We want to make sure our cell phone can do a speed test to the local speed test server while this network is down in terms of the satellite side. So let me switch to the camera again. Now you can see the dark side phone actually looks like it timed out because it cannot connect over the satellite link. But the other phone that's connected now to the same 5G network, but to the speed test server running locally, is still fine. So we can see that phone is still having no problems connecting. It's actually a little bit faster. You can see 214 megabits there. And then if we go back to our 5G software, the core, you will be able to see the throughput there to just show that this core is still active. It's still seeing the traffic going through that. So what we've shown here today is that we can actually have, as an example of these value-added applications on the OpenEdge, we can run a 5G core on there to provide a local network that can operate independently of the satellite link. So any questions on this? All right, good. So for the next part, I'm going to hand the baton over to Cody, and he's going to talk, let me just get that ready, about the multi-orbit. Thank you, Cody.
So multi-orbit at the edge, right? So I think we've all been there. It's one of those like really important online meetings, the kind where you show up a little bit early, maybe even wore a button-down shirt, and you turn your camera on right at the top of the hour. The president of the company is going over some big strategic initiative, and right as she looks at you, she says, "Gary, I'm going to outline the part that I need you to do." And then her face freezes like this. So you're sitting there like, oh my God, what am I supposed to be doing? And then right as she gets to the end, it comes back and she says, "Now I can count on you, right?" And of course you go, "Yeah, of course." You know, I had no idea what you committed yourself to, right? So in a single-threaded network, like a SATCOM network, things like this can happen more and more often. So at Kratos, we've been focused on solutions to help resolve that. And one of those is multi-orbit access at the edge. And I want to talk a little bit more about how we do that. So again, onboarding a third-party application. So in this case, we use ZipLink for its SD-WAN features in order to do some link aggregation and monitor networks. So you'll see over on the left side, we've got the ZipLink installed along with our virtual modem on that general compute. And then on the right side as well, we have the ZipLink appliance doing SD-WAN for that streamlining of the network resiliency. So as I talk a little bit more about this, I also want to point out the TV that we've got running over here on the left. So this is streaming a video that's being hosted on the server side, where we go through some of our capabilities. And I really want to see, as we do some simulations of network outages, if we can catch Kevin's face in one of those goofy expressions. So take a look and let's see what happens. So what we have here is we've simulated. We're running a GeoLink on our Edge remote, and then we have a simulated MEO link, LEO link, and a local ISP microwave link. So from a throughput perspective, the GeoLink is our highest throughput link, followed by the MEO and LEO, which are about equal, and then and they're all about 100 megs in one direction, and then the local ISP link is a 10 meg microwave link. And then from a latency perspective, this is the lowest latency, followed by the LEO, followed by the MEO, and then the GEO. And we've configured the SD-WAN appliance to evaluate traffic to see if there's enough throughput on the link to use it to do what we're trying to do. And if there's multiple options, use the one with the lowest latency. So if, for example, it's beyond 10 megs, but all the rest of them are up, it'll choose the LEO terminal. So Thomas, if you could you bring up that interface and I can talk a little bit more about that?
Yeah, so let's go to the zip link one. There you go.
Yeah, that's the one. Thank you. Okay, so the simulation's already running, but let me start out with this graph, right? So the graph here represents when it's in blue, that means the service is up and operational, right? So where we see blue in both my MEO and my Geo links, it looks like they're pretty solid. I haven't lost them at all through the whole thing. And then the black, this is my Leo link and this is my MEO link. Okay, so again, black means they were down. I never saw his face freeze. We'll see if it happens again, but and then we can see the traffic. So the traffic's been going this whole time, and that's what the traffic is up here. But each color is the different network. So this smaller one is that 10 meg local one that I talked about. And then green here is the Leo. I lose the Leo, I switch to purple, which is the MEO. And whenever we lose the MEO in a second, we're going to see the traffic seamlessly switch over to the Geo. So all of this is without any user intervention and no frozen face. I know exactly what they outlined that I need to do, and I think we're all happy in this more resilient solution. Any questions here? Yes, go ahead.
Just a quick question. So does sibling manage the changeover between the different links and types?
Yes. So it's monitoring the links and the uptime, and it actually kind of proxies that session, so it happens. That's how it happens seamlessly.
Mm-hmm.
Yeah.
Yeah, and just for the recording, so the question was, does ZipLink actually manage the different links?
Yeah, and that answer is yes. Go ahead. No, so good question. Yes, you can use multiple at this. If they're all, I think your question is, if all 4 links are up, are they all usable, right? Yes, they are. Actually, in this case, I'm stream balance. I didn't go into it much, but my actual rule is I stream balance the MEO and the Geo kind of all the time. And then it's that nested kind of logic loop of like, do I have enough throughput? It's going to try to use that Leo link if it's up because it's the lowest latency one, right, after the MEO. But it does take throughput into the fact it's like, okay, well, I've used all the lowest latency. Here's the next one that I should use next, if that makes sense. Yes.
Is that 3 separate software modems?
So in this case, we're in our scenario, we're saying that those modems are external. The Geo the Geo is in our edge, but the MEO and the Leo are separate. They're just connected via IP. And some of that is because there's proprietary waveforms that they don't let us run, right? I'd love to run them all in my own hardware, but that's why we simulated it that way. Yeah. Maybe someday we'll get there, right?
Great. Any more difficult questions for Cody? You can, yeah, sure.
One more question, Cody. You have set off your diversity, so you can use latency to decide which things to use. I'm assuming you can set up more complex rules.
Yes, absolutely. You can say real-time traffic, I want to do this way or what. So yes, there's a host of nested rules that you could say, hey, if this link is up and my video traffic, I want to always use this or whatnot. So it's all QoS definitions. So yes, you absolutely can.
Yeah, behind that there's a whole complex algorithms you can use and methods. This was just an easy way to show it. That's why we chose that way. All right, great. Any other questions? Yes. So.
Stations. You have a bunch of modems, you have a matrix switch, and you have an IFL to RF. Say you have a money transponder is a 200 modem. You don't know why it's expensive matrix you go LDAN, you go fiber, you go night, like a place that's there's a software available to take that function. But I have to pay $400,000 for matrix.
Yes. So the short answer is yes, right? So you asked about if I go to Diffie, uh, do I still need a matrix switch essentially, or can I do that all within the software? Uh, so it depends on where your digitizer is setting on whether you need let's say your digitizer is indoors and you're going to need the IFL to get it indoors into the digitizer. And then once you get to digital, you can route that to as many different locations as you need. So we've got a software channelizer combiner that kind of does that. It does that matrix for you, right? So it does the splitting or the combining, and that all happens in IP. Correct. So if you can do using digitizers at both places, you could do digital diversity site. Yes. It often is. A little bit of it has to do with throughput between, right? So if you can get dark fiber or whatnot, or how, it depends on how much you're trying to transport, right? But there is a cost of bandwidth, but yes, it's often cheaper than doing it the other way. Yeah.
Yeah, and you're welcome to come to us afterwards. We can show you how that works. There's another question. Yes. Oh.
When you stream balance the stream,
Yep.
sending the same stream from the 3 links.
No. So good question, but no. So a stream is on one link, right? So it doesn't like divide the stream and then send it over the one, right? So it's kind of like if you think of it just in the TCP terms, right? It's like each session could be put on each one, sort of thing. And then the stream balancing between those two, it actually does a ratio because there's like the throughput of one is 10 times what the other one was, so it puts one here and before it puts 10 there, sort of thing. Good.
Anything else? Okay, good. Thanks, Cody. So next up, we're going to talk about carrier monitoring. I'm going to hand it over to Bart. He's going to look at that, to talk us through that.
Ready?
I'm just going to set up the screen and then we should be good.
Great.
All right.
Thanks. Okay, yeah, so next we'll talk about carrier and spectrum monitoring on the edge device. So the challenge we run into is the satellite links are susceptible to interference. So even if you can virtualize everything or have a hardware modem, doesn't matter. If there's interference, the services could be disrupted fully or partially. So our solution is really to provide monitoring of the spectrum and the carriers at the remote edge. The benefit obviously is to restore the services. So Cody and Thomas showed you a variety of software functions that can reside on the remote edge. And today we'll talk about Monix carrier monitoring on the edge. So I think we can go into the... Thanks, Thomas. So Monix is very good about performing multiple functions. So visualizing the space segment and the carriers. So we can see here, even if we pretend that these two carriers are, for example, the gateway feed service carriers, and the other two carriers are the return carriers, we can also see a waterfall graph. This is very nice. And when we overlay the frequency plan, we can also see that the allocation is appropriately set up. So the carrier number 1 here is in its correct slot, carrier number 2 is in the correct slot, and so on and so forth. So this is very nice for a user either at the remote site or at the teleport, because they can see that the 4 carriers that are in the live spectrum are in the correct allocations. And when we introduce interference,
So we've got Azar behind the scenes here. He's going to introduce some interference. So we've got a bad carrier that's going to come in. And then Bart's going to show that.
Yeah, so it's very clearly visible that there is an interference occurring. But this is still a person sitting and staring at the screen, right? So we don't want to do that. It's not practical. So if we disable that interference, so now the interference is gone. And what we'll do is we'll ask Monix to perform those functions in the background. So now we have the spectrum back to how it was. The carriers are where they're supposed to be. And if we turn on the interference again, what we're looking for is for Monix to react automatically and on the blind. So now we see the red alarm came up, which is a notification that can let somebody know, hey, it's time to look at the spectrum and really dive in and examine what's going on. So if we turn that interference off again, two things will happen. The spectrum will clear and the alarm will turn green. So the benefit here is that these visualizations and the alarms are available to both the remote site user and to the gateway feed side service. So now both can coordinate to take action based on what they're seeing. And now we've also discussed multiple modems residing on the edge. So in this example, only one of the circuits was impacted, which means there's still communications back and forth between the remote site and the gateway so that they can coordinate and reestablish full services. So talking more about how Cody had it set up where we had multiple links running on an edge. That's it.
Okay,
Yep.
thanks, Bart. Any questions on the carrier monitoring side? Yes.
I'm assuming it'll take carriers that fall away that are supposed to be there, but also clear the carrier that is it's not supposed to be there.
Yeah, that's a great question. So Monix won't just alarm and say there is an issue. The type of alarm that comes up will indicate what the issue might be. So in your example, if one of the carriers goes away, it'll actually state missing carrier because it knows the database of the carriers that are supposed to be there. If a rogue carrier comes up, it'll actually say rogue carrier. And it can identify interference in empty capacity or on top or underneath the carriers that you're interested in protecting.
How many carriers can I monitor here on time?
Yeah.
How big a spectrum can I?
That's a good question. So with our newest digitizers, we're able to capture 500 megahertz of instantaneous bandwidth. So that allows you to perform time domain measurements at up to 500 megahertz. Of course, the device can stitch, so it can do frequency domain across multiple 500 megahertz chunks, yes. And typically, if you have multiple antennas, we would put an L-band switch in front, or you can have a dedicated digitizer for each of the paths.
Bart, could you touch on our digitizer lineup? Because you brought that up.
Yeah, so the new edge digitizers we have much faster digitizers. They're 500 megahertz, and we have a much better density. So we can actually stick 6 by 500 megahertz in a 1RU chassis. So you have a very high density.
Yeah, and we've got some examples here of the digitizers. So the three different ones. You're welcome to come and have a look at that.
And of course, the same digitizers are performing functionality to convert the L-band to IP packets for spectrum monitoring, for the software modems, for everything else that we're doing here.
Can you elaborate a little bit on your channelizer functionality? As far as I understand, spectral net receiver only does 2 channels from the 500 megahertz bandwidth. Any plans to add all in distinct channels or different?
Yes, yeah, that's a good question. So that's true. The digitizer has got 2 channels, so it can send the Diffie stream once it digitized the RF, send the Diffie stream in 2 channels out. But then we have a software module, a CNF called the channelizer, and that channelizer can take in that stream from the digitizer, and then you can break that down in up to 25 different channels. And then we normally, because it's software, if you need more than 25 channels, you can then stack them and just run multiple of those instances. In our SATCOM example, we actually used a channelizer to break down the specific carrier and then send that to the specific virtual modem that it needs to go to. So that's related to the other person's question there, that you don't need the RF switch anymore. In that case, you can use the channelizer. That's software. Okay, we'd love to talk some more and show you some more afterwards. That'll be great. Good. Any other questions? So that was great. I really like the interaction. So let's summarize quickly what we showed you today. So first of all, we showed the private 5G that can run on the edge. So on the OpenEdge at the remote site, it reduces your satellite bandwidth because it keeps local traffic local, and it stays up all the time. Doesn't matter what the state of your satellite link might be. We showed you the multi-orbit use case where we can increase capacity and give you the redundancy needed by making use of SD-WAN type software to use different links. And then we just showed you the carrier monitoring running on the edge, where normally it would be traditionally run at the teleport. Now you can have that insight on what's going on with your carrier at the edge, at the remote site, and provide better improved services and business continuity. So let's look again at the competitive advantages quickly to summarize that. So we can get lower cost by a reduced footprint. So you've got all these different applications that can now run on the same platform. You can increase efficiency because all these workloads on the edge can be run and share the services, share the infrastructure. And then very important, you can future-proof your investment because it's general compute running a standardized software virtualized environment. So now, for example, once you deployed, let's say, for example, this OpenEdge we have here with the private 5G and making use of the DVB S2X ACPC link, and later on you want to transition that to 5G NTN, you can keep the same hardware and everything at the at the remote site and just upgrade the software to support the 5G NTN waveform. So that's how you actually future-proof your investment. Now, inside Kratos, we do a lot of other different services and products we do offer across the satellite industry. There's some of the information you can look at, C2, orchestration, spectrum monitoring, as we saw, SATCOM, Earth observation, TT&C, gateway antennas. So those are not virtualized yet. That's still hardware you need to buy. And then NOC type services for things like geolocation, VSAT monitoring, and space domain awareness. So a lot of different products and services that we offer. We also have a complimentary copy of the Analysis Mation white paper here for you. Please feel free to grab one. This is a guide how to compete against all the new NGSOs, and it highlights some of the key competitive advantages of software ground. So please feel free to look at that. And that is it. Thank you very much for your time. Really appreciate it. I hope this was informative, and please feel free to come and talk to us afterwards if you have any questions.